Hello everyone. Welcome to this presentation on pipelining concepts. I'm going to discuss instruction pipelining and the various pipeline hazards that can arise. This topic falls under the broader area of digital logic and design, so let's get started. So, what exactly is pipelining? Pipelining is a technique where multiple instructions are overlapped in execution. This allows the processor to work on several instructions simultaneously, but at different stages of their execution. Think of it like a car assembly line. In an assembly line, different workers handle different parts of the car at the same time. This simultaneous activity increases the overall production efficiency. Similarly, pipelining improves the efficiency of a processor by allowing it to work on multiple instructions concurrently. Now, let's look at the typical stages involved in an instruction pipeline. Here is a common 5-stage instruction pipeline. The first stage is the instruction fetch stage, abbreviated as IF. In this stage, the instruction is retrieved from memory. The second stage is the instruction decode stage, or ID. Here, the instruction is decoded, and the required registers are read. The third stage is the execute stage, or EX. In this stage, the actual operation specified by the instruction is performed. The fourth stage is the memory access stage, or MEM. This is where memory is read from or written to if necessary. Finally, the fifth stage is the write-back stage, or WB. Here, the result of the instruction is written back to the register file. These stages allow multiple instructions to be in different phases of execution at the same time, increasing the overall throughput of the processor. To illustrate how pipelining works, let's consider an example timeline. Here we have 3 instructions I1, I2, and I3 going through a 5-stage pipeline across multiple cycles. In cycle 1, instruction I1 is in the instruction fetch stage, denoted as IF. In cycle 2, instruction I1 moves to the instruction decode stage, ID, while instruction I2 enters the instruction fetch stage, IF. By cycle 3, instruction I1 is in the execute stage, EX, instruction I2 is in the instruction decode stage, ID, and instruction I3 is in the instruction fetch stage, IF. This process continues with each instruction advancing through the pipeline stages in each cycle. By cycle 5, instruction I1 is in the write-back stage, WB, while instructions I2 and I3 are in earlier stages of the pipeline. This overlapping execution allows the processor to complete multiple instructions in less time than if they were executed sequentially. Each color in the table corresponds to a different stage in the pipeline, making it easier to track the progress of each instruction. While pipelining significantly improves performance, it also introduces certain challenges known as pipeline hazards. These hazards can disrupt the smooth flow of instructions through the pipeline, causing stalls or incorrect results. There are 3 main types of pipeline hazards. The first type is structural hazards. These occur when multiple instructions need the same hardware resource at the same time, leading to conflicts. An example of this is memory port conflicts. The second type is data hazards. These arise when an instruction depends on the result of a previous instruction that is still in the pipeline. A common example is read after write, or raw hazards. The third type is control hazards. These occur when the pipeline has to make decisions based on the outcomes of branches and jumps, which can lead to branch mispredictions. Addressing these hazards is crucial for maintaining the efficiency and correctness of pipelined execution. Let's dive deeper into data hazards with a specific example of a read after write, or raw hazard. Consider the following assembly code snippet. First, we have an add instruction that adds the values in registers R2, and R3 and stores the result in register R1. Next, we have a subtract instruction that subtracts the value in register R5 from the value in register R1 and stores the result in register R4. Finally, we have an OR instruction that performs a bitwise OR operation between the value in register R1 and the value in register R7 and stores the result in register R6. In this case, the subtract and OR instructions both need the value of R1, which is being written by the add instruction. If the subtract and OR instructions try to read R1 before the add instruction has written the result, we encounter a read-after-write hazard. This is because the subsequent instructions are dependent on the result of the first instruction, and the pipeline needs to handle this dependency to ensure correct execution. To mitigate the impact of pipeline hazards, several solutions can be employed. One common technique is pipeline stalling, also known as inserting bubbles or no operation, or NOP instructions. This involves pausing the pipeline to wait for the data dependency to be resolved. While simple, this method reduces performance. Another solution is data forwarding, also known as bypassing. This technique allows data to be directly bypassed from one pipeline stage to another without waiting for it to be written back to the register file. This maintains pipeline throughput and reduces stalls. Lastly, branch prediction is used to address control hazards. By predicting the outcome of a branch, the pipeline can continue filling with the most likely instructions, reducing the penalties associated with branch mispredictions. Each of these solutions plays a crucial role in optimizing the performance of pipeline processors. In summary, pipelining offers several key benefits. It enables higher instruction throughput, better CPU utilization, improved overall performance, and parallel instruction execution. These advantages stem from the ability to overlap the execution of multiple instructions through different stages. However, the success of pipelining depends on effectively detecting and resolving hazards through techniques like forwarding, stalling, and branch prediction. When implemented correctly, pipelining can lead to a significant performance boost, potentially improving performance by up to 5 times. Thank you for watching. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.